Okay, hello everyone. So today we're starting the gas unit. So it's our last unit of study for this course. And today's going to be a little introduction topic of what behavior gases perform, and as well as a review of the kinetic molecular theory. So actually this concept goes back to grade 9 even. But of course, I understand that it's been a long time. We did mention a little bit about this when we talked about chemical reactions, but we're going to go over this again. So this whole beginning part here is theory for the most part. Okay, so of course we know there's three states of matter: solid, liquid, and gas. So the main difference between each of the states has to do with really two things: the amount of energy that those particles have, and the amount of space between those particles. So solids have very little energy. Okay, so they have the lowest of the three, of course, and they have very little space between particles. So there's not much room for movement, let's say. Liquid has a little bit higher energy, so it's higher energy than a solid, but still less than a gas, and there's more space between the particles. Right, so now the shape can change, right? So constant shape for solids, right? It has a constant volume, not really compressible or changeable, at least not so much. Whereas a liquid, now because there's more space between particles, we're able to change the shape of that liquid, but the volume is a constant. So meaning I can't take something that takes up 100 milliliters of space and squish it down to now take up 75 milliliters of space. So whatever space it takes up is the same, but you can change the shape. So if I have that 100 milliliters in a test tube or in a dish or on the floor, right, they're going to take up different kind of shapes, right? And that's because there's more space between particles, so they can kind of slide over one another. Of course, gases have a very high amount of energy, so they're constantly colliding and bouncing around. And there's lots of space between them. So now, because there's so much space between them, we can compress a gas. So meaning we have space in between them that we can actually bring those particles closer together, and it can occupy a smaller space. So we can, for example, a propane gas tank, right? We can put a lot of propane gas in a small amount of space because we essentially push them closer and closer together. Okay, so I've already talked about this, but the forces between particles, right, have to do with their energy. But actually what is causing them to be close together or far apart has to do with the intermolecular forces, if you remember that from unit number 1. So things that have small amounts of attraction are going to be pretty far apart from one another. There's not an attraction between particles. The stronger and stronger the attraction is between particles, the closer and closer they are together. So if you think about it, solids have a high attraction for each other. They're very closely compacted together. Liquids have less attraction, and gases have the least amount of attraction. So what happens here is essentially things that are solids have very strong attractions. And the best example of that are ionic compounds. So if you remember when we talked about ionic compounds, the electrostatic attraction, so the positive negative ions, it's almost like little mini magnets with one another, right? Positive and negative attract. So when you have positives and negatives, they form that crystal lattice shape, right? So they're pretty much solid, all solid at room temperature. So when we say state of matter here, these examples, we're talking about room temperature, of course, because we know we can heat things up and, we can melt them or we can evaporate them, of course, right? So we're talking about room temperature for the most part. Okay, so polar molecules have a higher attraction, so they can actually come in a whole bunch of different forms, and it depends on how much of an attraction there is. So glucose, C6H12O6, has hydrogen bonds, and they're very highly attracted to each other. So actually it's a solid. Ethanol has hydrogen bonds, but it only has one hydrogen bond. It's a liquid. And then ammonia, even though it does have hydrogen bonds, the NH bond is weaker than the OH bond if you look at the difference in electronegativity. But really, at the end of the day, the state of matter, I'm just showing you that it varies. Ionic compounds are always solid, but polar and nonpolar molecules can come in a variety of states, because really every molecule, you have to look at each molecule on its own to predict the state, right? They all have kind of different situations. And then of course nonpolar molecules, which only have LDF, we know that the more LDF that substance has, so the bigger the particle gets, the more electrons and protons there are, so it becomes closer and closer together. So actually all three of these examples are nonpolar. But the smallest particle is a gas, the one that's a medium size is a liquid, and the one that has tons of atoms in it, this paraffin, which is a wax, is a solid. They all have nonpolar attractions, right, LDF, but the size of the molecule matters because it can have more, the more protons and electrons it has, the stronger the attraction is. Okay, so kinetic energy. So kinetic energy is essentially talking about movement of the particles. Okay, so there's three types of movements that particles can have. They can have vibrational energy, where it literally is like something vibrating, right? All particles do this. So solid, liquids, and gases, they all vibrate. So what that means is they're not really moving a lot. They're kind of just shaking around on the spot. Particles in liquids and gases have, and some solids, mostly liquids and gases, have rotational energy. So what that means is they're kind of spinning. Think of like how the earth is rotating, right? So particles can also rotate, but it needs a little bit more energy than just vibrational energy. So liquids and gases really do both of these things. And then of course, liquids and gases can also have translational energy. So what that means is they basically move in straight lines and they can collide or slide over one another. So this kind of shows you the pictures of what that's indicating. So vibrational energy is kind of just shaking on the spot, rotational energy is spinning, and translational energy is really moving in straight lines. And then it can collide with other things. So typically when we think of this, we think of gases, okay, but liquids also are able to move pretty freely. Okay, and of course you know that energy is impacted by the temperature of the particles, right? So it's directly related. So meaning, if you increase the temperature of a substance, you're going to increase the kinetic energy of that substance. And that just kind of makes sense. There's more energy available, so the particles are going to move more. And then the opposite happens. If you have particles that are now at a lower temperature, they're going to move less, right? So it's directly related to one another. Okay, so some properties of how gases behave. So the rest of this course is talking about how gases interact with other things. So we have to kind of overview what properties of gases are. So of course we know gases will fill the container. So whatever container you put a gas in, it's going to spread out and fill the entire space. We know that gases are fluid, right? And that goes back to the fact that they are able to move in all three ways. So gases can move quite freely. Gases have a low density. Okay, so what that means is if you were to compare the density of a gas to a density of a solid or a liquid, right? So remember, density is really talking about, let's say we had two containers. Oh, Lord. This is not the time to start making fun of my drawings, okay? So let's say we had here, this was a liquid and this is a gas. Density has to do with a ratio of mass to volume. So because gases have more space between particles, right? So even though there's space between particles in a liquid, I'm doing a really bad job at this. In the future, I'm just going to find a picture of this. But okay, gases have more space between particles. So density has to do with mass in a certain volume of space. So because let's imagine these are the same amounts of space. Because liquids and solids can have more particles in that space, their mass is going to go up. So gases are automatically going to be lower in density because they're not going to have as many particles in the same amount of space, right? So if I have a glass of water and a glass of air, I'm going to have way more particles of the water because air has naturally more space between the particles. So I just can't fit as many in the same amount of like square footage, if you want to think of it that way, right? So like 100 milliliters of water versus 100 milliliters of air, there's just going to be less particles in the air because there's more space between them. So if you think about if you were to compare a liquid to a solid, the solid would be more dense because you would have more particles compacted in to the same amount of space. Gases are compressible, so we already mentioned that. Because there's so much space between the particles, we can actually push them to be closer together to take up less space. And then gases are miscible. Okay, so if you remember that term from when we looked at solubility, that means that gases can mix with other gases, right? And you can't really make, so like gases are homogeneous mixtures. So if you think of air, for example, air has nitrogen and hydrogen and water and carbon dioxide, oxygen, right? It has a whole bunch of different gases, but air all looks the same. It's mixed evenly, right? They are soluble with one another. So gases are miscible with other gases. Okay, and then linking the kinetic molecular theory to gases more specifically. So of course, particles of matter are always in motion. We know that. Solid, liquid, and gas, particles are always moving. The volume of an individual particle is approximately 0. Okay, so what this means, this is an assumption that we are making. So what that means is that the size of an actual particle of gas, so let's say oxygen. We're saying that one molecule of oxygen is so small that we assume that it is almost 0 volume, right? Like, we're talking about one individual particle. So imagine for a second if I were to have, right, I'm talking about, here is a container with gas in it, one dot is representing one oxygen molecule. We have no way of measuring what the volume is of that one particle. So we just say, the volume, it's so small we can't even measure it. We're going to make it 0. Now, in real life, does it have 0 volume? No, of course it's going to take up space. We just have no way of measuring it or even estimating it because it is so small. Okay, collisions of particles with the walls of container cause the pressure exerted by a gas. So what that means is, let's say you have a gas inside of a container, the gas is going to bounce around, kind of like in this picture, it's bouncing around. The more collisions that happen with the container, like the actual outside container, the higher the pressure will be. So the next video I'm going to talk about pressure, but essentially the more collisions that happen, the higher the pressure is. So if there is a lot of collisions, you have a lot of pressure of that gas. We'll come back to that. Average kinetic energy is proportional to the temperature. We already covered that, right? So the higher the temperature, the more movement those particles have. And then particles exert no forces on each other. We're going to talk more about this later on in the unit, but essentially it's assumed that particles don't push each other around. They kind of act independently of one another. So like this collision is not being impacted by this collision over here. They're acting like their own beings. Okay, so that's not actually entirely true. We'll talk about why that is later on in the week. But for now, this is like another assumption that we make. Kind of like how this is an assumption, this is also an assumption.